So this is going to be an example problem for two objects that are connected together in some way. And in this example, they're going to be connected by a string that I've showed. And you have to imagine these are two bottles of water that are hanging, and there's some pulleys that are supporting these strings. And I'm not showing the table here that the pulleys are resting on. But there's a single string that connects these two objects. Now, the problem that we're doing is a good example that you can use for any other problem where we've got two or more than two objects that are all connected in some way so that their motions are connected. Now, in this problem that we're doing, because there's just one string connecting these two, every time this mass goes down a certain distance, say 1 centimeter, this mass has to go up by that same distance as long as this string doesn't stretch or break, and as long as it remains tight. So they both move the same distance in the same amount of time. So at all times, both of these masses, because they're connected, have to have the same velocity, and because they have the same velocities at all times, they also have to have the same accelerations at all times. Now, it is true that one of them will have a downwards velocity while the other one has an upwards velocity, so I really should have said they have the same speeds because their velocities are in opposite directions. And I should say that the magnitudes of their accelerations are equal, even though the directions are going to be different in this example. But that will always be true for situations where two objects are connected together. The magnitudes of their velocities and their magnitudes of their accelerations will be equal. Okay, in this problem we have a heavy bottle with a mass of 1 kilogram and a light bottle with a mass of 0.6 kilograms. And if I release this, if they're not resting on anything, we know that the heavy one is going to accelerate downwards, and at the same time the light one's going to accelerate upwards. So I'm going to draw that on the diagram. I'm going to draw his acceleration, A, and I'll go ahead and draw his velocity direction. That will also be downwards. This guy over here will have an acceleration upwards and a velocity upwards. I don't have to put the subscripts heavy and light on the velocity and acceleration because both objects have the same amount of velocity and acceleration. Okay, we're going to do the force diagrams. The forces on this heavy mass are going to be a tension from the string and Earth pulling down with a gravitational force, M heavy G. And we're going to do the forces on the light object. That's going to be a string holding that one up, and M light G. We're going to make our positive direction always with the direction of each object's acceleration. So that's going to be downward is positive for this heavy guy, upward is positive for the light guy. We're going to do our net force equation that goes with the force diagrams. So the net external force for the heavy guy, I'm going to put a subscript on that because each one has its own net external force, is going to be M heavy G with a plus sign minus tension. That net force, those two forces added together make the net force. Newton's second law says that net force must equal m of the heavy guy times his acceleration, a. Now, I'm going to show you an algebra trick whenever we have two or more net force equations. We're going to write the net force equation for the other object, but you'll see why I'm going to do this. I'm going to put it directly underneath the net force equation for the first one. So I'm going to write the net external force on the light object. That will equal T with the plus sign minus m light G from his force diagram. All that must equal m light times a. Now, I wrote them lined up vertically because what I'm going to do now is add the two equations. And this is going to be an algebra trick that's very useful when you have connected objects. We're going to add the left sides, and we're going to add the right sides. And we'll make a new equation by adding those. So if you look here, if you add all of these left sides, all four of these things, it's going to make a new equation that's really simple. Because here we have minus t, and here we have plus t. And t is the same for both objects. So those are going to cancel out in the math. So all I'm going to have is the other terms left. So if I add all the left sides to create a new equation, that must equal the sum of all the right sides. And the right side is also going to be simple because I have the acceleration a, or the magnitude of that acceleration a, which is the same for both objects. So we're going to factor out an a and make the right side also very simple. So I'll do that on the next page. Alright, I'm going to add these two equations. Adding the left sides, I get mhg minus t plus t minus mlg. If I add the right sides, I get mha plus mla. Well, minus t plus t is 0. Right here, I've got mhg minus mlg. Well, I can factor out g. That will be mh minus ml times g. And on the right side, I've got mha plus mla. Factor the a, you get mh plus ml times a. So now it's really easy solving for, if you wanted to know the acceleration, you just isolate a. It is mh minus ml times g over mh plus ml. Now we'll put in some numbers. mh is, the heaviest one is 1 kilogram mass. ml is 0.6 kilograms. All that times g, which we'll put 9.8 meters per second squared. Let's see. I'm going to estimate because I don't have my calculator. That is 0.4 kilograms over 1.6. 0.4 over 1.6 is 1/4, and 1/4 of 9.8 is 2.45 meters per second squared. I think I did that right. So that is our acceleration. If we wanted to know the tension in this problem, we could then go back to one of our original equations, either one, and isolate t. So I'm going to take the second net force equation and solve that for t down here. Now that I know the acceleration, t must be m light a plus m light g. And so that's m light, which is 0.6 kilograms, times a, which is 2.45 meters per second squared, plus g, which is 9.8 meters per second squared, and all that, if you work it out, that turns out to be about 7.5 newtons. And that answer should make sense if you go back and look at our original force diagrams. We know that the weight of the light guy is about 6 newtons. If he's going to be accelerating upwards, that means the net force must be upwards. So the tension has to be greater than 6 newtons to make an upwards net force on the left guy. And 7.5 newtons is greater than 6 newtons. Also, this guy must accelerate downwards, the heavy one. His weight is about 10 newtons. And the tension has to be less than that to make a net force downwards for him to cause him to accelerate downwards. So this problem was an example of two connected objects where what you do is write their separate force diagrams and their separate net force equations, but if you write them vertically and then add the two sides, stuff will usually cancel out, making the algebra simple. If you've listened this far, there's one other nice thing you can know for this problem, if you go back to our formula for the acceleration, even if we hadn't subbed in the numbers, we can look at our algebra and make some sense out of that. For example, this formula would allow us to find what the acceleration would be in any situation. What if the two masses were equal? How much acceleration would there be if the two bottles had equal mass? Well, you can see right away that if I put in mH equal to mL, I'm going to get 0 over something, and that should make sense. We would have an equilibrium situation if the two masses were equal. You can also imagine what would happen if one of the masses were 0. What if we didn't even hang a mass on one side? Let's say the light mass is 0. Well, if you put in m light is 0, then you get mhg in the numerator divided by mh in the denominator. And so you'll see that A would just be G, which actually makes sense, because if you didn't hang a light mass, you just had a heavy mass attached to the string, there actually wouldn't even be any tension in the string because nothing's hanging off the other side, and you would have a free-falling heavy mass, and its acceleration would be G. So by doing our formulas and not putting in the numbers till the end, you can actually apply our formula to lots of situations and see that the physics actually does make some sense here.